All right, we're about to jump into something that connects the ancient world to the absolute cutting edge of tech. It's all about this one fundamental idea, this sort of universal formula that we humans have been using forever to figure out our world and even reshape it. So let me ask you this. What could ancient ink, Latin grammar, and something like ChatGPT possibly have in common? I know, it sounds like the setup to a really nerdy joke, right? You've got this physical goo, a dead languages rulebook, and one of the most advanced AIs on the planet. I mean, they couldn't be more different. Or could they? Well, here's the secret sauce. They're all about the same human impulse. This obsession with finding the code to take our world apart, see how it ticks, and then, well, rebuild it. And that's what we're calling the universal formula. It's this drive we've always had to deconstruct something, figure out its rules, and then put it back together, maybe even better than before. Honestly, it's the engine of all innovation, taking us from, mashing up plants for color to literally programming artificial brains. And once you see it everywhere. I mean, really think about it. You've got ancient alchemists trying to boil everything down to its basic elements. You've got linguists diagramming sentences to find the hidden logic. And physicists, they're still searching for that one theory of everything. It's all the same game. Find the rules. Find the system's code. Okay, so to make this super clear, let's start with something you can literally touch. We're going to decode nature itself. And we'll begin with something that seems so simple, something we've had for thousands of years: ink. How in the world do you get the color out of a plant and make it stick to a piece of paper? So the story of ink, it goes way back, like 4,500 years ago in Egypt. Super simple formulas back then, basically charcoal and glue. For centuries, that was the deal. We used what nature gave us. Then, boom, 1856 hits, and synthetic dyes are invented. Suddenly, we have all these crazy new colors, and we can mass produce them. But now, it's funny, the pendulum is swinging right back. We're getting really interested in natural dyes again, mostly because we're thinking more about health and the environment. And this really shows you the core trade-off, right? On one hand, you have synthetic dyes. They're cheap, they're efficient, a total product of us re-engineering chemistry. But they can be pretty rough on the environment. Natural dyes, they're the total opposite. They're biodegradable, way less toxic, because they're designed to work with nature's chemistry, not against it. And that brings us right back to our main point. To get that beautiful natural ink, you can't just, smash a flower and call it a day. You have to follow a process, a recipe, a formula to pull out that one specific thing that holds the color. You have to deconstruct it. Let's take a beet, for instance. Look at this process. It's basically a kitchen chemistry experiment, right? First, you grate it up to get more surface area. Then you soak it in a solvent to literally pull the color molecules out. You filter away all the pulp, and finally you let the solvent evaporate. And what's left behind? That's it. That's the pure formula for red that was hiding inside the beet, the betine dye. Okay, so that's a beet. But what's so wild is that we apply this exact same thinking to things you can't even touch. We do it for totally abstract systems, like language. I mean, get this. There are actual research papers out there with titles like An Algebraic Approach to Latin Grammar. They're literally trying to use math to define the rules of a language. So from plants to grammar, the mission is the same: find the code. And that, of course, brings us to the ultimate abstract system, the big one, intelligence itself. How do you even begin to find the formula for a thought? Well, this is where modern AI comes in. The whole approach is to deconstruct the brain's most basic building block, the neuron. Now, in an AI, a neuron is actually way simpler than you might think. It's really just a tiny math machine. It takes some numbers in, does a little calculation, and spits a new number out. That's it. So, for example, a network could take in your age as a number, and a single neuron's job might be to process that number to help decide, say, if you're a good candidate for a YouTube premium ad. So here's the little formula inside that neuron. It gets an input, like your age. It multiplies that number by a weight, which is just a fancy way of saying how important is this piece of info. Then it adds a bias, which is kind of like a little nudge to push the final decision one way or the other. And finally, it runs that result through an activation function. That's the final rule that makes the call, like a simple yes or no. The most basic kind of activation function is called the Heaviside function. Just think of it like a light switch. It's either on or off. So for our YouTube example, the rule could be dead simple. If the final number is 18 or higher, flip the switch to 1 for on. If it's less than 18, flip it to 0 for off. Easy, right? It's a binary yes or no world. Yeah, but the real world isn't always so black and white, is it? As the saying goes, a patient isn't 100% healthy or 100% sick. There's a whole spectrum in between. A simple on-off switch is just too clumsy for complex problems, like, say, medical diagnosis. So we need a smarter formula, and that's where something called the sigmoid function comes in. Instead of a hard, clunky switch, this thing produces a nice, smooth S-curve. The output is always a number somewhere between 0 and 1, and you can think of that number as a probability. So now the neuron isn't forced to say yes or no. It can say, there's a 0.7 or a 70% chance that this patient is healthy. And that ability to handle nuance, that's a total game changer. Okay, so we figured out the formula for a single tiny neuron. But the real magic, the power of AI, happens when you link millions of these things together in a massive network. See, a network's job isn't just to make one little decision. Its job is to learn the deep patterns hidden inside mountains of data. And how does it learn? Well, it basically does two key things to the data it sees. It performs what are called linear and nonlinear transformations, and these are the two moves that let it make sense of the world. So a linear transformation is the simple one. It can rotate the data or stretch it, but lines stay straight. The best way to think about it is like turning a paper map. The map is still flat, you're just looking at it from a different angle. But the nonlinear transformation, that's where the real magic is. This is like folding or crumpling the map. It lets the network bend and warp the data in complex ways. Why would you do that? So you can find these complicated, curvy patterns that a simple straight line would miss completely. It's like folding the map to bring two very distant cities right next to each other. So how does it know how to fold the map? It learns through this process called training, or more technically, backpropagation. And it's basically a simple loop repeated millions of times. Step 1, it makes a guess. Step 2, it checks how wrong it was. There's a special loss function for that. Step 3, it works backward and figures out which of its little internal knobs, the weights and biases, were most responsible for the mistake. And step 4, it just slightly adjusts those knobs to be a little less wrong next time. That's it. Guess, check, correct. Over and over and over again. So this whole cycle, this constant guessing and checking and correcting, what is it? It's the network's automated way of searching for the perfect formula. It's letting the machine do the discovery for us. At the end of the day, all that complicated training is just one thing, a massive automated search. The network is searching for the one perfect set of numbers, the best values for all its weights and biases, that creates the perfect mathematical formula to solve the problem, whether that's spotting a cat in a photo or writing a sonnet. And that right there brings our whole journey full circle. You see? It doesn't matter if we're using chemistry to pull the formula for color out of a plant, or using algebra to nail down the rules of grammar, or using this crazy training process to let a computer discover the formula for learning. The fundamental process, the human impulse, is exactly the same. Deconstruct the system, find its rules, and then use those rules to build something new. It's this incredibly powerful pattern that has taken us all the way from natural ink to artificial intelligence. We've managed to decode nature, language, and now the very basics of learning itself, which leaves us with a pretty mind-bending question, right? What's the next great complex system that humanity will try to write the formula for next? Thanks for joining me on this one.